Hey there, YouTubers! Oh man, I so much love my Jewel Pod. Oh man, ever since my local coffee shop allowed me to smoke my Jewel, it's been so great. I just love my nicotine addiction. Hi there, Dr. Sheep here. Welcome back to another physics video. Now, I figured when I came up with the idea for this video that it'd be easy and fun. I was wrong. I was so wrong. Energy is far more complicated than I could have originally imagined. But I'll explain what we're actually going to talk about, like the main points, in the next cut. Okay, so energy is a property of matter, much like inertia. Energy, like momentum, must be conserved. It may seem like in certain systems energy is being destroyed, but in actuality it's changing into a different form. I'll explain those different forms in a minute. But let's focus on the basics for now. So can you measure energy? Yes. It is measured in joules. 1 joule is equivalent to picking up a 1 Newton object to a height of 1 meter. A 1 Newton object has the mass of 0.1 kilograms. So there is potential energy and kinetic energy. Potential energy is the energy within an object. More on that in a minute. Kinetic energy is the energy of a moving object. This has one set equation. Ke is equal to 1/2 times m, the mass of the moving object, times v, the velocity of the moving object, squared. Okay, so from here we continue to break down energy into 6 sections: macroscopic, microscopic, light, entropy, dark matter / dark energy, and energy resources. Now I'm not going to cover all of this in today's video, just macroscopic. Also, you'll probably see the other parts, maybe. I don't know. Macroscopic energies are the ones we're usually the most familiar with. The first one I'm going to talk about is gravitational potential energy. You can calculate the gravitational potential energy of almost anything. Gp is equal to g, the acceleration due to gravity, or on Earth 9.8 meters per second squared, times m, the mass of the object, times d, the distance between the object and the ground. Take this baseball, for example. It has a mass of 0.145 kilograms. Take that times 9.8 times its distance from the ground, 2 meters, and it has a potential energy of 2.84 joules. This number makes a lot of sense if we think about the units for joules. Okay, the next type is mechanical energy. This has 3 categories to it: translational, rotational, and vibrational. Translational is standard linear kinetic energy and is represented by that earlier equation. Rotational is the kinetic energy of a rotating object. Okay, so this is where things get weird. Ke rotational is equal to 1/2 times the moment of inertia. This is the mass of the rotating object times the distance between the axis and the force causing the rotating object, causing the rotation, squared. Take your moment of inertia, I, times w. This is the angular velocity. This is revolutions per second, and square that. Now on to vibrational kinetic energy. This can come in all shapes and forms, but is usually just sound. However, sound deserves its whole own video, so I'm not going to touch on that today. Why, hello there. I have my fun fact book. I'm in my fun fact chair. That means it's time for another fun fact. So what kind of fun fact could I have about energy? Well, when calculating gravitational potential energy, G can actually change. That's not actually the gravitational constant. See, every planet has a different mass. Therefore, that affects how fast you accelerate towards that planet. Therefore, that number changes. So on the moon, your gravitational potential energy is at the same height you would be on Earth is much less. And for Jupiter, which has a much higher acceleration, your gravitational potential energy would be much greater than the Earth and much greater than the moon. And then say a black hole, well, that's even crazier. Isn't that just fascinating? This next type is elastic potential energy. This is the energy that is stored in a spring or rubber band when compressed or stretched. This comes down to the hydrogen bonds in the material. Unlike most hydrogen bonds, these will bounce back into place if not too much force is applied. This is also why rubber bounces. Now, there are many fancy equations for this, and they all have to do with specific materials and specific situations. So, I'm going to just move on. These last two I'm going to sum up in the same cut. The last two are electrical energy and magnetic energy. Electrical energy powers almost everything in the modern era. It comes from the imbalance of positively charged and negatively charged particles. Electrical energy can either be potential or kinetic. Capacitors, which we have explored before, have potential electrical energy. When this energy moves, we call it current. This is kinetic electrical energy. Magnetic energy is generated when a current is run through a conductive material. This energy attracts specific metals. These specific metals are called ferromagnetic, and at relatively close to room temperatures, there are only four: iron, cobalt, nickel, and gadolinium. That last one isn't actually ferromagnetic at room temperature, but is still ferromagnetic at just a few degrees cooler. That's it for today.
Oh, cool.
Thank you, Phil. Anyways, again, I don't know when or if there will be other parts to this, so stay tuned. But in the meantime, I would like to thank you all for watching. Please like, comment, and share. New videos every other Friday, 4:30 p.m. Central Time, and good night. Oh, you're still here? I thought I told you to go home. Oh, you want more? Well then please subscribe and hit the bell icon so you know every time I post. And while you're there, check out the playlist. Oh, you're still not satisfied? Well then check out my Instagram for exclusive content. And if you really want to help me out, you'll stick around for the next 20 seconds to give me that sweet watch time. Bye.